All right, if you've made it this far, good for you. We're in the last video now for completing our constraint analysis, just for our preliminary um, conceptual design for our aircraft. So we've done stall, takeoff, climb, with two different ways of calculating climb, whether that's the rate of climb or the climb angle. And we looked at cruise. We talked about how we normalize the cruise thrust to weight values to bring it back to our takeoff conditions, so we're comparing apples to apples. So since the last video, I just kind of cleaned this up a little bit, just so we can easily translate between the values in our table and our graph. I just added color to the headings and removed some color, so we have these dashed white lines so we know which ones are the dashed lines, which ones are solid lines. And it's just easier to depict and view which are the parameters that we're looking at. So now I can easily tell right away that this curve here corresponds to cruise. It's blue and it's a solid line. So this is our cruise when we're accounting for our weight difference in our laps. This solid orange line is our stall for a clean wing with no flaps, and then this stall line here is stall with our flaps fully extended. So the last thing we have left to do is total landing distance. And the method I'm going to show and go through is based on what is presented in the Raymer textbook. So I'll show you the equation from the text, depending on the units you're using. So we're using British units, foot, pounds, seconds. So I'm going to use the top equation here. So the total landing distance is going to be equal to 80 times our wing loading times 1 divided by our density ratio and our maximum lift coefficient, plus this SA. This SA term is your approach speed, or your approach distance, and it's going to change depending on the type of aircraft you have. So typical aircraft, commercial aircraft, we can approximate their approach based on a 3-degree glide slope. So it's a 3-degree angle of approach over a 50-foot obstacle. And so just by geometry, the distance approximately, including your flare and your touchdown, this value is going to be approximately around 1,000 feet, or 305 meters. So that's the estimation that Raymer suggests to use. So we have 1,000 feet plus this parameter over here that we're going to calculate. And then one more thing, if we have a aircraft that's going to be certified under Part 25, then we should take that total landing distance requirement and we should divide it by 1.67. So the reverse of what is in the text. This equation is if you wanted to estimate the landing distance. The textbook suggests add 67% or multiply by 1.67 to your total landing distance you calculate to give the required safety margin. So if the requirement that we have has the safety margin built in, then we have to try to design to a more stringent landing distance. So we're going to take the requirement that we have, divide by 1.67, and that will be our actual landing distance. And then we just rearrange this equation to solve for our wing loading, and that would give us our wing loading required for landing distance. Now notice this is not a function of thrust to weight ratio. This is because typically in landing, aircraft are coming in near idle. So there's no dependency on your thrust to weight ratio if you're not producing any thrust during this segment of flight. Also, for certification, you need to assume that you have to be able to land within a certain distance without the use of thrust reversers. So if you have thrust reversers, then you could land in a much shorter distance once you have touchdown. The reason you can't include that for your analysis is in the event that you come into landing and maybe one or all of your engines are inoperable, you're coming in with a true glide. If you're depending on thrust reversers to be able to land in a certain distance and you don't have access to those because they're not working, they're broken or something, then you still need to be able to land within a certain distance. So for certification basis and the point of constraint analysis, we need to design our aircraft with an appropriate wing loading so that we could land without thrust reversers in this distance. Again, this is approximation. When you would go and do your performance analysis, you would go into more detail based on what is on your aircraft, and you would calculate a total landing distance, a ground roll, braking distance, and then you would look at the effect of adding things like spoilers and thrust reversers to see how much you could improve the performance. So for now, we're just applying this equation. So let's copy over. Just going to make one more heading. Should just need one more line. And so what I'm going to do, I'll call this section landing. And so I don't confuse myself, this is going to be wing loading that it's plotting. So our equation, if we think of reversing this, we're going to take our total landing distance, which is our requirement. So our requirement is up here. We have a total landing distance. Just input this as 8,000 feet. So this is our takeoff distance. I think I just assumed that we'd be taking off and landing from the same airport. Yes, so our landing distance over a 50-foot obstacle I have right here. So we'll equal that, and I'm going to divide. Oh, forgot to click equals. It's going to equal our landing distance, and I'm going to divide this by 1.67 just to see what that is. So the landing distance that we should be able to stop within and be adequate to provide sufficient margin safety, then we're aiming for 4,790 feet for our total landing distance, which is, not crazy. So then we're going to subtract our approach distance, which is 1,000 feet for a commercial aircraft or Part 25 aircraft, to approximate. Now I'm going to put these terms in brackets, and I'm going to divide by 80, and I'm going to multiply by our density ratio. So if we're going to do this at sea level conditions, our density ratio is just going to be 1. So I'll just leave that out, and then multiply by our maximum lift coefficient, and I'm going to assume this is with fully flaps deflected. Having more flaps, more lift during takeoff, or sorry, landing, have the double benefit. You're also generating more drag, which will help slow you down. So let's say we have our maximum lift for our landing condition, and that should be it. We hit equals here, and we have our wing loading required to land in this distance is 94. Now that's quite high compared to the values we're seeing over here, 25 or so. Now this doesn't mean we have a stringent requirement. It means that we only need to have, or we can have up to a wing loading of 95 roughly pounds per square foot before we can no longer land within this distance. So if we wanted to just sort of back calculate and approximate, if we wanted to get a wing loading of 25, which matches our stall condition, our landing distance, we could probably reduce this quite a bit, even more than that. So this aircraft probably, reasonably, with a safety margin, 67%, have a landing distance of about 3,500 feet. It's far better than its takeoff distance. But for now, let's leave it at 8,000. Assume it's taking off and landing from the same airport. So again, copy this down, but I'll just dollar out all the values so it doesn't change. And because we're plotting wing loading again, all we have to do is select 2 points. So we'll call this landing, and this is at sea level. X values are just going to be our 2 wing loading values, and our Y values are just going to be 0 and 1. Plot this, and we see this point appear way out off in the distance. So now let's say we want to land at a high altitude airport and at high temperature maybe. So we're landing in Denver in the summer, 5,000 feet, and maybe it's 100 degrees out. So how do we account for that? Well, that can be accounted for through our density ratio. So if we copy over this equation, move it one more. I'll add this was at sea level. I guess I've been adding them down here. This is at sea level. And now I'm going to add at 5,000 feet hot, let's say. So these all have to be corrected. Shift them left one column. Now, where our density ratio value is, I have to add a term. So I'm going to multiply by a density ratio that corresponds to 5,000 feet on a hot day. So our density ratio is just a density at the condition divided by density at sea level. So I don't have a density ratio parameter, but I've already calculated using a non-standard temperature the density at 5,000 feet on a hot day. So plus 30 degrees is plus 30 degrees Fahrenheit, or Rankine, same scale when dealing with a temperature change, not absolute temperature. So the density at 5,000 feet, if it wasn't a hot day, 0.002048 slugs per cubic foot. When it's a hot day, this decreases slightly, so we have slightly less density on a warmer day. So I'm going to have equals to this value, and I'm going to divide it by the sea level condition. So that'll give us our density around 0.74, I believe, something like that. So equals, so in this case, if we were to try to land in Denver and we needed to land in an 8,000 foot runway, we couldn't exceed a wing loading of 77 pounds per square foot and be able to land within the distance of that runway safely. So let's plot this as well. Select our data. So we have landing. I'm going to put Denver. Wing loading and 0 to 1. Whoops, 0 to 1. And so it moves it further to the left. So anything that's moving these curves upwards and to the left is making the requirement more strict. Let's say it's limiting the size of our design space. So ideally we would like these curves to all be far to the right and very low, so we could have the smallest engine possible, the lowest wing load or lowest thrust to weight. And usually it's desirable to have a larger wing loading. If you have a larger wing loading, it means you tend to have a lighter wing. And that's just because you have less wing required to generate the lift needed. So if you have a higher wing loading, you don't need to have the wing relative to the size of the aircraft like a glider. Having a large wing adds weight to the aircraft. It also adds a lot of structural constraints because now you have this large wing. If you want to maintain a reasonable aspect ratio, it's a large cantilevered beam. So you're adding load further and further out. So it has compounding effects that forces you to increase the weight so you can withstand the structural requirements of having that larger wing and more distributed load. So that's pretty much it for the constraint diagram. It's not a whole lot more. Once you have this, just a matter of tinkering a little bit to understand the sensitivity of some of these parameters, going back to your designs, making sure that the values you have are reasonable, and then using this to try to select, at least at a preliminary stage, an optimal thrust to weight ratio and wing loading. So for this aircraft, it looks like, based on the numbers that I've just pulled out of a hat, a good wing loading would be somewhere around 20 pounds per square foot. And then we could probably get away with a thrust to weight ratio of maybe 0.18 would be something reasonable, give a little bit of a buffer. So I'll leave it to you. Enjoy playing around with this. Once you have this tool, there's quite a bit you can do, and hope to see you around next time.